Hello class, in the last video we learned how to name ionic compounds, but those ionic compounds that we learned how to name contained only monoatomic ions, and we classified them into type 1 or type 2 based on the cation, whether the charge is a single charge or a multiple charge. Today, we are going to, in this video, we're going to learn about naming ionic compounds that contain polyatomic ions and not monoatomic ions. So when we say polyatomic ions, we are referring to the fact that these ions contain more than one atom. Okay? They contain more than one atom. Now, when we name these ionic compounds, we have to take into account that first, whether they contain polyatomic ions or not. When we named them, the anion naming ended with IDE, if you recall. What are polyatomic ions? Let's take a look right here a little bit on some of these polyatomic ions. You notice most of them contain oxygen, and they start with non-metals. Some of them contain metals, and we'll talk about those. So let's take a look at a way to help you memorize these polyatomic ions. I know I can tell you just memorize them. There's a list for you on Canvas. Under that page, you need to memorize this info for Chem 10. But let me see if I can help you here find a pattern from the periodic table and some variations on it in order for you to have an easier time learning this stuff. So let's take a look at the periodic table here. We haven't learned about this yet, but we will down the line. That fluorine, for example, likes to pull electrons to itself when it's combined with other elements. And the noble gases, these noble gases right here, don't like to interact with any other elements. And fluorine likes to pull electrons to itself. Therefore, when it combines with other elements, it's not going to be a central atom. So we can exclude fluorine for now. If we look at the other elements, notice I told you with the polyatomic ion, when we looked at them, when we looked at the polyatomic ions, most of them contain oxygen. Notice? Oxygens everywhere. So how can we learn a pattern from the periodic table, add in stuff to oxygens? So let's take a look on how we can do this. If I look at, we already decided we're excluding fluorine. So the two elements that are closest to fluorine, excluding oxygen, since we're adding oxygen to other stuff, would be nitrogen and chlorine. So I'm going to start with these two, and I'm going to walk you through a pattern to see how we can get through this. So let's go through that pattern. If we take chlorine, okay, that's chlorine, and give it a charge, we change the end name to chloride. You'll recall that, right? So we change the ending to IDE. But if we were to, instead of giving it a charge by itself, we're going to add oxygen to it. So with chlorine, we are going to add oxygen. And the basic number of oxygen to be added to any of these elements is going to be 3. So we're going to end up with this. So this will be chlor, like we did here, chlor. Then we added IDE. Instead, we're going to add ATE. Okay, so it'll be chlorate. That's how you deal with polyatomic ions, chlorate. You would expect that if we do the same with nitrogen, should be same thing. So let's do that with nitrogen. So I'm going to go NO3 minus, and that would be nitrate as well. These two are going to be our anchors. I'm going to start here and there. Then we're going to see how moving away from these will help us find a pattern. So as we move to the left, we are going to keep the same number of oxygen, but we're going to increase the charge. So that next to nitrogen, there's carbon. So I'm going to go CO3, it'll be 2 minus. Then next to carbon will be boron, it'll be BO3, 3 minus. This is called carbonate. Carbonate, and this is borate. Carbonate and borate. So as we move to the left, charge will increase. Okay, a charge will increase. If we move down a row, now we're moving down a row to chlorine, and as we move to the left from chlorine on the periodic table, not only the charge will increase, but we add one more oxygen. So as you move to the left, you add an oxygen, and the charge will increase. So we go ClO3 minus, that's chlorate, then will be SO4 2 minus, and that will be sulfate. Then with phosphorus will be PO4 3 minus. That'll be phosphate. Notice how we went from right to left. The charge increased the same way we did up here. And then we go down here, the charge will increase as well, with increasing the number of oxygen to a maximum of 4. Those are the patterns you can get from the periodic table. Now, since chlorine is this, so everything below these that I just gave you, 1, 2, 3, and the 1, 2, 3 up here, those are the bases. Then anything below them will experience exactly the same pattern. So take a look. With chlorine, if we go down below that, that would be bromine. So that should be BrO3 minus, and that's bromate. With iodine, it'll be IO3 minus, and that's iodate. Now for sulfur, right below sulfur, there's selenium. So SeO4 2 minus. That'll be selenate. And right below phosphorus, you see there's arsenic. So it will be AsO4 3 minus. And that is arsenate. These are some of the patterns. Hopefully will help you recognize these things and make it easier to memorize polyatomic ions. We'll talk about some more patterns. Now, so let me share with you how we name these things and how we use the polyatomic ions in terms of charge cancellations and so on and so forth. So we have KNO3. Potassium is a type 1 cation. Nitrate is the name of this polyatomic ion. We just learned that it's a nitrate. So the name will be potassium nitrate. But if we look at FeOH2, we recognize this is a an ionic compound with Fe being a type 2 cations. Since OH is the hydroxide, we're going to learn this. This is part of what you need to memorize. OH is a hydroxide. It has -1 charge, and since I have two of them, I am going to get a total of 2 negative. That means the charge on Fe is 2 plus. So we're going to name it as iron 2 hydroxide. We look at NH4NO3. We have two polyatomic ion. NH4 is an ammonium ion, and Na3 is a nitrate ion. Therefore, the name will be ammonium nitrate. Let's look at this example right here. Aluminum ion, so let me write that down. That'll be Al3 plus with a sulfate ion. That's SO4 2 minus. In order to make this compound, it's going to be Al. The charge on the sulfate is 2 negative, so I'm going to put 2 subscript for aluminum. And since sulfate is a polyatomic ion, I need to put it in parentheses since I'm going to have more than one. So that'll be parentheses SO4. Now, the charge on aluminum is 3 plus. That means the subscript for the sulfate ion is 3. Therefore, the formula will be Al2SO4 3. Now, let's look at chromium 2. With chromium 2, let me see if I can fit both. For chromium 2 ion, this is the formula, Cr2 plus, and hydrogen carbonate, that is the formula right here, hydrogen carbonate, 2 plus, -1, that means I need 2 hydrogen carbonate. 2 hydrogen carbonates are needed, and the formula will be as such. Since hydrogen carbonate is a polyatomic ion, it must be surrounded with a parentheses in order to indicate that I have 2 of them. Now let's look at some variations of the polyatomic ion. I'm going to start with the common, how do I exit out of here? There we go. We learned that NO3 is the base, that's nitrate, SO4 2 minus is the sulfate. So if I have 1 oxygen less, then the name is going to change the ending to ITE instead, ITE. So notice right here, NO2 minus becomes nitrite. SO3 2 minus becomes sulfite. That's going to be true for the rest of the elements. Let's look at chlorine here. We started with chlorine with 3 oxygen and it gave us chlorate. If we were to lose an oxygen, it becomes chlorite. And if we were to lose 1 more oxygen, okay, so we lost an oxygen from chlorate to chlorite. If we were to lose an extra oxygen, it's still going to be chlorite, but in order to indicate that we lost an extra oxygen, we add the prefix hypo in front of it. So it'll be hypochlorite. If we were to gain an oxygen going from chlorate, ClO3 to ClO4, we added an extra oxygen in there, then we go and it should be hyperchlorate, but historically we dropped the HI and now we call it perchlorate. Perchlorate. Notice the same is true for bromate. BrO2 minus is bromite, BrO minus is hypobromite, and BrO4 minus is perbromate. The same is true for the iodine group. I hope this makes it clear. Other patterns. Anytime we add a hydrogen, we're going to think of the hydrogen as H plus. Okay, we're going to think of the hydrogen as H plus. Notice the charge right here on the carbonate is CO232 minus. If I were to add an H plus to it, I'm going to neutralize that charge. It's going to neutralize one of the charges, and it's going to be negative right there. It'll be negative, and we're going to call it hydrogen carbonate. Alternatively, we can use the older name, and instead of calling it hydrogen, we can call it bicarbonate. And you need to know that as well. Bicarbonate. This is the pattern that I just outlined for you up top. Now you can see it. Let's take a look at some examples of naming. Well, actually, we did look at naming polyatomic ions. For now, all I can tell you, please memorize those as soon as possible. Make flashcards and take a look at the lab. We are doing this lab as a take-home lab. It's an exercise. Use this lecture, read the lab instructions, and fill out all the lab informations on there. And I'll give you more instructions on the lab, how you're going to turn it in. I will create an area on Canvas for you to upload your labs. I'll correct them and give you feedback from there. That's for naming ionic compounds. And we are done with naming ionic compounds. Now we're going to move to naming molecular compounds. Okay, when we say molecular compounds, we're talking about non-metal, non-metal. We don't have metals anymore. So we have two or more non-metals in our molecular compounds. Unlike ionic compounds, where the charges indicate how many electrons have to be transferred from one species into another, therefore we can come up with the formula, and there's only one formula to describe the combination between the cation and the anion. In molecular compounds, there are many, many different combinations at which these things come together. Therefore, we need to indicate how many we have of each in the compound. So we're going to use a different convention to name in molecular compounds. And the convention is as follows. We're going to name the name of the first element and the name of the second element, but instead of using the name of the element, we're going to use the name of the anion. Therefore, it's going to be ending with IDE instead. In order for us to indicate how many we have of each, we need to use prefixes. Okay? We need to use prefixes. So each elemental name is preceded by a prefix to indicate how many we have. Now, in order to keep this simple, we're going to keep it to only binary compounds, only 2 elements in each compound, no more. Binary compounds. Okay, binary compound. Now, when it comes to prefixes, we are not going to use the mono prefix for the first element. We'll do it for the second, but not for the first element. On the first element, we do not use the mono prefix. Okay? We do not use the mono prefix. These are the prefixes. It's mono for 1, di for 2, tri 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. When we use these prefixes, if the name of the element starts with a vowel, we are going to drop the O, the A's from the prefixes, not the I. So these two, we will not drop the I, but for the rest of them, we are going to drop the A's as well as the O from the prefix. And we do not use mono prefix for the first element. Okay, we do not do that. Notice right here we have carbon dioxide. For carbon, we don't say monocarbon dioxide. It is carbon dioxide. So we used the prefix for the second element, the stem of the name, and we end it with I, D, E. You look at N2O, it is dinitrogen oxide. Dinitrogen oxide. Now, you notice we didn't say monoxide. That's because that's the common name. Even though we should dinitrogen monoxide, but the common name is this. But we're going to keep it in this class. We are going to call it dinitrogen monoxide. Dinitrogen monoxide. Let's take a look at BF3. That would be boron trifluoride. Okay, it's boron trifluoride. If we look at NO2, that is, we don't call it mononitrogen, but it's nitrogen dioxide. PCl5 is phosphorus pentachloride. Phosphorus pentachloride. I have 5 chloride, therefore it's pentachloride. For this one, it's diiodine. Diiodine. I have 2 I's. Diiodine. 7-fluorine, that's heptafluoride. Heptafluoride. Right? Diiodine heptafluoride. That's naming molecular compounds that are not acids. In other words, they do not start with a hydrogen. Acids, on the other hand, are molecular compounds. There are molecular compounds, and we're going to learn about acids when we get to chapter, I believe it's 15 or 14, chapter 14. They're molecular compound that forms ions when they dissolved in water. They start with a hydrogen. That hydrogen is what causes the ionization in water. And we're going to categorize them into 2 groups. Binary acids. And when you say binary acids, we mean the hydrogen and another element, like HCl, for example. That's a binary acid, 2 elements only. That's a binary acid. Or an oxyacid. When we have a polyatomic ion with an oxygen, like HClO3, that's an oxyacid. We have a hydrogen with a polyatomic ion that contains oxygen. That's an oxyacid. We have one convention to name binary acids, and we have another convention to name oxyacids. All right, let's take a look at how we name binary acids. Now, the naming here is simple. We're gonna take the name, so let's take HCl. Now, historically, the first scientific definition of an acid only looked at compounds that when they dissolved in water, this AQ right here means that dissolved in water, when dissolved in water, acted in certain manners. So it indicates that those are only acids in water. So when we name them based on that historical definition, we have to include the hydro in front of it to indicate that they are in water. So we start with hydro prefix. Then we're going to use the base of the name of the element that is attached to hydrogen. In this case, it is chlorine. So we're going to use chlor. Then we're going to add a suffix to it, ic, followed by the word acid. So that would be hydrochloric acid. And that's how we name binary acids. All right, it'll be hydrochloric acid. Same is true for bromine. It'll be called hydrobromic acid. We need to add that AQ after it. See that AQ? In order to indicate that it's dissolved in water and to differentiate it from the compound when it's not acting as acidic, when it's in gaseous state, for example. So HCl right here, it's hydrogen chloride molecule because it's in the gaseous phase and it's not acting as an acid. Now, the number of hydrogens in an acid have to do with the charge on the anion. We know that Cl has one charge, Br has one charge, so they're going to combine with only one hydrogen. So we can have HCl and HBr. Sulfide, on the other hand, -2 charge, so we're going to need two H pluses in here to give us H2S. So hydrogen sulfide in the gaseous state, if you put it in water, it becomes hydrofluoric acid. Hydrosulfuric acid. Becomes hydrosulfuric acid. Two hydrogens. Now let's talk about the next oxyacid, how we name oxyacids. Those oxyacids are based on the polyatomic ions that you guys are supposed to memorize. We talked about earlier in this video. So if we were to add hydrogen, the number of hydrogens you add to come up with the acid is going to be equivalent to the charge on that element. So let's take a look at what we have here. Nitrate, -1 charge, we added 1 hydrogen. Sulfate, 2, this is sulfate. Sulfate 2, we added 2 hydrogen. All right, so that H plus ion depends on the charge of the oxy ion. The formula must always be neutral. So when we name oxyacids, we're going to use the following convention. We are going to look at the name of the anion, that polyatomic ion. If it ends with ITE or ATE, we have different conventions. If it ends with ITE, we are not going to use hydro here. Notice, no hydro. We're going to just use the base name of the oxyanion, and we're going to add to it OUS at the end, followed by the word acid. For example, H2SO4, it is H2SO3, that's the ite, okay? It's sulfite, SO3 2 minus is sulfite. It's sulfite. So when we name this as sulfurous acid. Sulfurous acid. If the name ends with ATE, so if I had SO4, 2 minus, it is sulfate, not sulfite, it's sulfate, then the name will end with ic instead. So it's not, instead of sulfurous acid, it's sulfuric acid. These are some common oxyacids. Nitric acid, because the anion is nitrate, will give us nitric acid. If I had nitrite, then it'll be nitrous acid instead. This is carbonic acid, comes from carbonate. Carbonate, carbonic acid. Take a look at this table. Hopefully this would allow you to have an idea how to name these acids. In the nomenclature, we have a section in the lab that deals with hydrates. So let me go over that with you quickly, what hydrates are, then we can name some. Hydrates are basically ionic compounds that get contaminated with water molecules. So if you live close to the beach, there's a lot of humidity in the atmosphere and things get moisture. That moisture will seep into the compound and intercalate between the different parts that make up that ionic compounds, right? Remember we talked about how it forms a crystal lattice. It would actually intercalate between the lattice points of that crystal lattice and give us a hydrate. So if we look at this one, for example, that's a compound. When we name it exactly the way we've been naming stuff. So that's magnesium sulfate. But now we need to indicate how many water molecules we have. We're going to use the same prefixes we use to name molecular compounds. So I have 2 of them right here. So that would be di. And water, because those are hydrates, we're just going to call it hydrate. Dihydrate. Okay, so it's magnesium sulfate dihydrate. We can look at this compound. This is copper 2 sulfate hexahydrate. So we have 6 water molecule, so therefore it's hexahydrate. We use the same prefixes that we've used earlier. Let's see if we can name these acids right here. This first one right here, H2S, we don't have an oxygen. It's not an oxyacid. It's a binary acid. That means we need to use the prefix hydro. So we're going to call this hydrosulfuric acid. This is an oxyacid. The polyatomic ion right here is chlorate. Therefore, this is chloric acid. This is also an oxyacid. And that polyatomic ion is a nitrite. Therefore, this is nitrous acid. Nitrous acid. nitrous acids. Now, when it comes to writing formulas for acids, it's always based on what we learned how to name it. We're just going to reverse engineer that. We're going to go back with it. Anytime the name ends with acid, then the formula must start with an H. You write the formula as you write an ionic compound. In other words, you need to match the number of H's of what you think is the charge is going to be on the anion. Even though it's the molecular compound, but it helps thinking of it that way. If it's only a binary acid, then you add, it has a hydro prefix in front of it. That means it's binary. And if it's no prefix, then it's an oxyacid. For oxyacids, if it ends with ic, then the polyatomic ion must end with ATE, and if it ends with OUS, then the polyatomic ion ends with ITE. Let's take a look at an example. Hydrosulfuric acid. So if we look at hydrosulfuric acid, that means we're starting with hydrogen. We look at the sulfide, right? It says hydro, that means we have a binary acid, and sulfuric means we have a sulfide. So I'm going to use the sulfide ion, it has 2 negative charge. That means I need 2 hydrogen. The formula will be H2S, and I need to add aqueous after it. Let's look at how we do it with carbonic acid. Carbonic acid, there is no hydro. That means it must contain a polyatomic ion with an oxygen in there. So we're going to look at carbonic, ends with ic. That means it's carbonate. The name ends with ATE. It's a carbonate ion. That's CO3 2 minus. Excuse me. The charge on the proton is +1. That means I need 2 of them. The formula will be H2CO3. H2CO3. Sulfurous acid, on the other hand, there's no hydro. It's a polyatomic ion, and it's sulfur because ends with OUS. That means I must have a polyatomic ion that ends with ITE. For sulfur, that's 3 oxygen. The charge is still -2. I need 2 hydrogen for that. Therefore, the formula will be H2SO3. All right, let's take a look at some more examples. So for chlorous acid, no hydro, it's a polyatomic ion, ends with OUS. That means the polyatomic ion is 2 right here, not 3. 2, -1. That means I need only 1 H plus. The formula will be HClO2 aqueous. Phosphoric acid, it's also a polyatomic ion. It ends with ic. That means it's a phosphate ion. I need 3 hydrogen for that. The formula will be H3PO4 aqueous. For hydrobromic acid, that's a binary acid with a bromine, H plus and Br minus. The formula will be HBr aqueous. All right. Before I conclude this lecture, I need to go back to the polyatomic ions. We looked at all the polyatomic ions that have their center is a non-metal, but sometimes we can have polyatomic ions with a metal center. So let me go back and revisit those quickly. Excuse me. On that table. There we go. You have a list on Canvas that gives you a complete list. That's the one I'm going to hold you responsible for, but let me highlight a few of them here. So that would be chromate, that's a metal center, CrO42 minus, dichromate, Cr2O7. Let me add the other ones that I'm going to need you to know. Let me add them right here. So in addition to chromate, I am getting a new tablet. This one is, I'm having a hard time writing on this. Just give me hopefully next week I'll have better writing abilities. CrO42 minus is chromate. Cr2O7 2 minus is dichromate. Then we have some one more metal center. MnO4 minus, and that's permanganate. Then we have OH minus, that's hydroxide. I have H3O plus hydronium. We have Cn minus, and that's cyanide. CnO minus, cyanate. SCN minus, thiocyanate. We have O22 minus, peroxide. And let me see what else. What else am I missing here? Chromate, manganate. Okay. We have C2O4 2 minus, oxalate. C2H3O2 minus, acetate. And there are some more. They're all listed on Canvas, so please go back there and look at all of them. So let's now conclude the lecture by summarizing everything we have looked at. In order to name chemicals, we must first determine what type of compound we're looking at. If it's ionic, molecular, or an acid, we follow different rules. If it's ionic, we need to determine if it's type 1 or type 2 cation, if it contains type 1 or type 2 cations. If it contains type 1 cation, all we have to do is simply name the cation followed by the name of the anion. That's it. If it's type 2, then in addition to naming the cation, we must include, using Roman numeral, the charge on the cation, then followed by the name of the anion. For molecular compounds, on the other hand, all we have to do is simply use prefixes to indicate how many we have. We need to change the ending of the second element name and use instead the name of an anion rather than the name of the element. And when it comes to acids, we need to determine whether we have a binary acid or an oxyacid. If we have a binary acid, we need to use a hydro prefix, hydro, followed by the base name of the element, ending with ic, followed by the word acid. For oxyacids, we need to determine if the name of the polyatomic ion ends with ITE or ATE. If it ends with ITE, then the ending of the acid will be OUS. If it ends with ATE, then the ending of the acid will be with IC, and both will be followed by acid. And until next time with the next chapter.